Adipose tissue is not an isolated depot of stored calories. It is an active, communicative organ engaged in a continuous neuroendocrine dialogue with the brain and peripheral organs. This dynamic crosstalk positions adipose tissue as a central coordinator of whole body homeostasis, seamlessly integrating energy intake, nutrient availability, metabolic demands, and even behavioral states. Through hormones, cytokines, and neural signals, fat cells provide the central nervous system with real-time updates about the body's energy status, while simultaneously responding to top-down commands that govern metabolism, appetite, stress, and circadian rhythms. One of the most iconic examples of this neuroendocrine relationship is leptin, a hormone secreted by adipocytes in proportion to fat stores. Leptin travels through the bloodstream to the hypothalamus, where it binds receptors in the arcuate nucleus, triggering responses that suppress appetite and increase energy expenditure. When fat stores are high, leptin signals satiety and promotes energy usage. When fat stores are low, leptin levels fall, stimulating hunger and metabolic conservation. This feedback loop ensures that energy balance is maintained over time, adapting behavior and physiology to match fuel availability. But leptin is not simply a hunger hormone. It is a key regulator of neuroendocrine axis, affecting reproductive hormones, thyroid function, immune responses, and even cognition. Leptin deficiency, as seen in rare genetic conditions or in extreme starvation, disrupts not only eating behavior but also growth, fertility, and immunity, revealing the far-reaching influence of adipose-derived signals on systemic physiology. In the aging process, leptin resistance, where the brain becomes less sensitive to leptin's signal despite high levels, may contribute to metabolic dysregulation, inflammation, and altered satiety control. Another major player in this neuroendocrine web is adiponectin, also secreted by adipocytes, particularly in metabolically healthy fat. Unlike leptin, adiponectin levels decrease in obesity. It enhances insulin sensitivity, reduces hepatic glucose production, and promotes fatty acid oxidation in muscle. Through its action on the brain, liver, and pancreas, adiponectin fine-tunes glucose metabolism and protects against insulin resistance. Its anti-inflammatory and anti-atherogenic effects further highlight adipose tissue's systemic protective roles when functioning properly. The relationship between adipose tissue and the pancreas is also tightly regulated. Free fatty acids and adipokines from fat modulate insulin secretion from pancreatic SS cells and glucagon release from A cells. Healthy fat tissue buffers nutrient excess, preventing spikes in circulating lipids or glucose that would otherwise stress pancreatic islets. In conditions of lipotoxicity or fat dysfunction, however, this communication becomes distorted, leading to insulin resistance or SS cell exhaustion. Thus, properly regulated adipose tissue is not a threat to metabolic health, it is a crucial safeguard. In addition to hormonal signaling, there is emerging evidence of neural innervation within adipose tissue, especially through sympathetic and sensory nerves. Sympathetic neurons release norepinephrine to stimulate lipolysis, releasing fatty acids when energy is needed. Conversely, sensory nerves in fat tissue detect local metabolic status and transmit signals to the brain, contributing to energy balance regulation. This bidirectional neural communication implies that adipose is not merely responsive to brain commands, it actively informs them. In fact, recent research suggests that some of the earliest satiety signals may originate from fat via sensory nerve activity before food intake is fully processed. The neuroendocrine integration extends even to the hypothalamic pituitary adrenal (HPA) axis, which governs the stress response. Chronic stress elevates glucocorticoids like cortisol, which act on adipose tissue to influence fat distribution, lipolysis, and adipokine secretion. In turn, adipose tissue modulates the stress response through cytokines and steroid metabolism, providing feedback that can either resolve or perpetuate the stress signal. This interplay is especially evident in conditions like visceral obesity, where stress-driven fat accumulation creates a feedback loop that impairs insulin sensitivity and promotes inflammation. Circadian rhythms further influence adipose neuroendocrine functions. Adipocytes express circadian clock genes that regulate their secretion patterns and metabolic activity. Disruption of sleep-wake cycles or irregular eating patterns can disturb the rhythmic release of adipokines, contributing to metabolic disorders and weight gain. This underscores how tightly fat function is interwoven with central nervous system timing and behavior. When adipose tissue is metabolically flexible and functionally intact, this neuroendocrine crosstalk promotes adaptation and resilience. Fat cells adjust their hormone output in response to feeding, fasting, activity, temperature, and stress, helping the organism survive and thrive across a wide range of conditions. Far from being a liability, fat serves as a high-bandwidth signaling hub, processing metabolic inputs, sending behavioral cues, and maintaining physiological balance. In this context, adipose tissue should be appreciated not merely as storage, but as a vital endocrineural interface, both sensing and shaping the organism's metabolic destiny. Its failure leads to systemic dysfunction, but its proper function provides a cornerstone for health and longevity. If protected and nurtured, healthy fat is not something to fear, but something to value as a communicator, a regulator, and a guardian of whole body harmony.